given the following functions f and g, please find f plus g of x and f minus g of x. So if I wanted to add these two functions, this is one way I could write down the notation. And you read this out loud, you say f plus g of x. And this means exactly the same thing as f of x plus g of x. F of x is x squared divided by x minus 1. G of x is 1 divided by x plus 1. And if I wanted to add these, I just have to find a common denominator to add my fractions. So you find a common denominator by multiplying this by x plus 1 over x plus 1, and multiplying this one by x minus 1 over x minus 1. And this becomes x cubed plus x squared plus x minus 1 over x squared minus 1. So it's weird notation, but if you see parentheses f plus g, parentheses x, that's f plus g of x, and you just add the two functions together as they're defined. And you want to simplify too, right? So if this was multiple choice, I wouldn't make this choice A, I would make this the answer choice in the multiple choice, right? So I do expect you to do some simplifying once you add your functions. So then the other thing you can do is subtract these functions. I could say, what is f minus g of x? And that is just f of x minus g of x. And you proceed doing everything exactly the same way, right? F of x is x squared over x minus 1. G of x is 1 over 1 divided by x plus 1. And then you would find a common denominator, and the common denominator would be the same thing. It would be x squared minus 1, and you would just subtract instead of add whenever you add those, or subtract those fractions, right? And that's what it would look like to subtract fractions. So the only new thing you really have to get used to today, the only thing we haven't already done this semester, is just to look at that notation and say, yeah, I'm subtracting these fractions, and this is how I plug them in. Does that make sense? In the next exercise, we'll also multiply and divide these functions. I keep saying the word fractions today. We're talking about functions. So if I wanted to multiply these functions, what you might see is like this. We say f times g of x. And this is just f of x times g of x. So this would just be 3x plus 5 times 2 minus 1 over x. I also want you to simplify if you get to this point. And you know the way that I like to multiply. Whenever I have a factor with more than one term, is I multiply like this. I say 2 times 3x is 6x. 5 times 2 is 10. 3x times negative 1 over x is negative 3. Yeah, because the x's cancel. And then negative 1 over x times 5 is negative 5 over x. So then I write 6x. Perfect. And that is a mixed form of a rational function, so that's something I would consider to be a simplified form. I would just probably make that be the answer on a multiple choice question. Okay, so we feel good about multiplying functions. The last thing I might do is divide functions. Last thing for this example anyways. And so if I see this, I think f divided by g of x. And this is just f of x divided by g of x. Let me double check and make sure that's... Oh, actually, this one wants g divided by f of x. So if I want g divided by f of x, it would be the same idea. It's g divided by f of x. It's g of x over f of x. So g of x was 2 minus 1 over x. And I'm dividing by f of x. This is not quite in a simplified form, so I can tell that this is a rational function, but it's not in expanded form, it's not in mixed form, it's not in factored form. I want you to put it in a simplified form. Any one of those three is totally fine. Maybe the easiest way to do this is just to multiply by x over x. And then I get 2x minus 1 divided by and this would be an expanded form of a rational function. So that could be your first answer. Okay, so you just plug in your functions, you simplify, and that's how you add, subtract, multiply, divide. The next thing on our list today is function composition. And be very careful, because if I were to write this, that tells me to multiply the functions. But if I write this, that tells me to compose the functions. You see the difference? I use little bullets for multiplying, but I use tiny little rings for composition. And that's a common mistake I see. People will see this and they'll try to multiply. But this is what function composition means. If I wanted f composed with g of x, this is saying do f of g of x, like that. This reminds me of a YouTube video I saw 15 years ago. It was around Thanksgiving. And the guy was like a home cook, and he was making a turducken. He cleaned up his chicken, and he cleaned up his duck, and then he stuffed the chicken inside the duck, where the duck has the hollow out spot. And then he cleaned up his turkey, and he stuffed the duck inside the turkey. So there was a chicken inside of a duck inside of a turkey, and then he cooked that, roasted that. He called it a turducken. Same idea with function composition. You take this function, whatever comes second, and you stuff it inside the argument of the first function. So, if my f function is x squared minus 6x plus 9, I'm going to write g of x squared minus 6 times g of x plus 9. I just replaced the x's in my f function with g of x because that's what's sitting in the argument there. But then g of x is just the square root of x. So this is square root of x squared minus 6 square root of x plus 9. And what is the square root of x squared? X. So f composed with g of x is that. All right, what if I wanted to do the reverse order? What if I would say g composed with f? Function composition is not commutative. You know, it doesn't matter the order in which you add or multiply because addition and multiplication are commutative. But it does matter the order in which you subtract or divide because those are not commutative. Function composition is also not commutative. And so it matters what order you compose these things. And so my g function was the square root function, right? So I write down my g function, which is the square root function, but I replace the x with f of x, because that's what's now in my argument. Well, the f of x function was x squared minus 6x plus 9. It is a perfect square. So that factors as x minus 3 squared. And so I would say g composed with f of x is x minus 3. You can also take a function and compose it with itself. So if I ask you what is g of x, and g is just the square root function. So I take the square root of g of x, which is the square root of the square root of x. That's the same thing as the fourth root. Yeah. So g composed with g is the fourth root. You could also do f composed with f. It would take a long time. Because you got a lot of multiplication to do if you try f composed with f. But you could do it. It's possible. I just don't want to do it in class because I don't want to waste time. And I think you already have the idea of what composition does. When you put one function inside the argument of another function, that's how it ends up. There is something that you have to know about, at least, called the difference quotient. And to be perfectly honest, the difference quotient is very useful in Calculus 1. But if you're not going to take Calculus 1, you probably don't ever care about this. I don't know why it's necessarily introduced in algebra whenever you can just save it for Calculus 1. But there is a question like this on your final exam. You don't need to memorize that, right? On the final exam question, it actually tells you what the difference quotient formula is, so you don't have to memorize this. It will be given to you. But nevertheless, there is a question that's similar to this on the final. And it says, find the difference quotient of this function, and this function is the x squared function. And to find my difference quotient, I need to know what is f of x plus h and f of x, and then divide that by h. So f of x plus h is not quite. It would be x plus h squared. So I've got to replace the x from my original function with my new argument, x plus h. Okay. Excuse me. that means when I go to plug in this stuff into my difference quotient formula, I'm going to write x plus h squared minus x squared over h. But I want you to simplify this, right? This is not fully simplified yet. X plus h squared is going to give me x squared plus 2hx plus h squared. So I've expanded that part. If I want to go on simplifying, what would I simplify next? Yeah. Positive x squared cancels with negative x squared. And I get that. Yeah, I can divide both of those terms in the numerator by h, and I get 2x plus h. That's as simple as it gets. So that is my difference quotient. So here is the full story about Calculus 1, right? If you ever take Calculus 1 or you have a friend that's telling you about his Calculus 1 homework, Calculus 1 students have to take the derivative of a function. The derivative just means you find the difference quotient and then you set the h equal to 0. Okay? So in the Calculus 1 story, we would say the derivative of x squared is 2x, because I just set the h equal to 0. But the reason this is an interesting question for Calculus 1 students is you can't just set h equal to 0 from the get-go, right? Like if I tried to not simplify this and I wrote x plus 0 squared minus x squared, I would get 0 in the numerator. And the denominator is h, so it's 0 in the denominator. I have 0 divided by 0. That's like nonsense, right? So the trick is you write the difference quotient and you simplify it all the way. And then if you're in calculus, you set h equal to 0 to get your derivative. But you don't have to know that. Y'all are not calculus students, so it's just a little preview. So we'll do this again. Now my function is 1 over x. And I know that as I'm trying to find my difference quotient wants f of x plus h minus f of x divided by h. F of x plus h would be perfect, 1 over x plus h. So this is 1 over x plus h minus 1 over x divided by h. And here in the numerator, I'm subtracting 2 fractions, so I should find a common denominator, yeah. So let me multiply the first fraction times x over x, and I get x over x squared plus hx. And then the second fraction I'll multiply by x plus h over x plus h. So I get this. And then I would subtract, right? So x minus x is just 0, and then minus h, because you've got to distribute that minus sign, is going to give me minus h over x squared plus hx divided by h. Now, remember, dividing is the same thing as multiplying by the reciprocal. So if I want to take this fraction and divide by h, I could just multiply by the reciprocal of h. And then this simplifies to perfect. That is the fully simplified difference quotient. And again, remember the calculus 1 part of the story that you don't really need to know is that if I set h equal to 0, I get the derivative. So if I have the function 1 over x, the derivative of 1 over x is negative 1 over x squared. But the Calculus 1 students, they can't just set h equal to 0 right off the bat, because if they were to set h equal to 0, they would get 1 over x minus 1 over x. They would get 0 in the numerator. They would get 0 in the denominator, and it would be nonsense. So the calculus students have to simplify the difference quotient all the way before you can finally set h equal to 0. And that's why maybe we're making you guys do this in algebra, so that you eventually have a recollection of this in the future. But any questions about how we did this? All right. So more definitions. An even polynomial is a polynomial where you write it out in expanded form, and all of the powers of x are even numbers. But you're also allowed to have the power of 0, even though 0 is not really an even number, which means we're allowed to have a constant term. Here's an example of an even polynomial. Right? It doesn't matter what your coefficients are, but the powers of x are even numbers, and I'm also allowed to have a constant term, like plus 17 if I want to. This would be even. This is an example of an odd polynomial. It doesn't matter what my coefficients are. What really matters is what the powers of x are. And I'm allowed to have a term with just x, because that's like x to the 1 power. And so my powers of x are only odd numbers here. You're not allowed to have a constant term for odd polynomials. Most polynomials, you'll realize, are not even or odd. So in general, polynomials are not even or odd. They could have a mixture of some powers of x that are even and some powers of x that are odd. So don't expect polynomials to be even or odd. Most of them aren't. But the great thing about even and odd polynomials is that these odd polynomials have rotational symmetry about the origin. Whenever you graph the curve on the xy plane, odd polynomials have rotational symmetry about the origin, and even polynomials have bilateral symmetry about the y-axis. So this is about symmetries in the end. I could give you the polynomial x to the 4th minus x squared. That's an even polynomial. Even if I add a constant term, it's still an even polynomial. And that means it's got symmetry, bilateral symmetry across the y-axis. It looks like it's a mirror image of itself across the y-axis. And that's true for all even polynomials you can think of. You see the symmetry? What's slightly harder to see is odd polynomial symmetry. So like here's an odd polynomial. If you were to take this graph and rotate it 180 degrees around the origin, right? So imagine you put a push pin down right at the origin, you take the curve and you spin it around halfway, then that is the same curve before and after the rotation. Do you guys see that? How the valley on the right side, you rotate that around, it would become the hill on the left side. Okay, that's odd symmetry. So that's how it works for polynomials, if they have all even or all odd powers. We can extend this idea to functions now, that some functions aren't polynomials. There's 3 functions right there that aren't polynomials. But we say an even function is any function that has bilateral symmetry across the y-axis. just like the even polynomials do. And we say that an odd function is just a function whose curve has rotational symmetry about the origin, just like the odd polynomials do. Again, just like polynomials, most functions are not even and they're not odd either. But we can look at a few pictures. Like, is this function even or odd, or neither? So it's even if it has bilateral symmetry across the y-axis. Like if it looks like a mirror image of itself, left and right, that would make it even. So this is an even function, because it looks like a mirror image of itself. What about this function? Is that even or odd? Or neither? You say even? Is that a mirror image of itself across the y-axis? No. It's actually odd. If you were to rotate this picture 180 degrees around the origin, you'd get the same curve. Someone in my last lecture didn't believe me. So there's something you can do if you have Microsoft Word available. Just copy and paste your graph, and then grab the rotation thing, and then rotate it 180 degrees. And then you can compare them side by side. And say, yeah, that looks like exactly the same picture. I just rotated this one. I didn't rotate that one, but it still looks the same. What about this function? Is that even, odd, or neither? That one is neither. It's not a mirror image, it's not a rotation, it's neither. What about this one? Even, odd, or neither? Odd. Very good. Yeah, you can rotate that, get the same picture. What about this one? Even, odd, or neither? Even. What about that one? Odd. Yeah. So the cube root of x is an odd function, so I can rotate. What about this one? Neither. Yeah, square root is neither. Cube root is odd. The fourth root is neither. The fifth root is odd. All odd roots are going to be odd functions. What about this one? Even. Absolute value is an even function. So, if you don't have Desmos available, like on a test, you can't just pull out your phone and check. Here's how you could test, right? A function is even if you plug in negative x into the argument, you simplify it, and you get exactly the same function back. That's how you can tell it's even. A function is odd if you try plugging in negative x for the argument, and you simplify everything as much as possible, and you get the negative of your original function. That's your even odd test for functions. So this first function. If I want to test whether this function is even or odd, I start by plugging in negative x, and I get 3 to the power negative x to the fourth. But negative x to the fourth is the same thing as positive x to the fourth, because you have an even number of minus signs you're multiplying through. And so that is the same thing as the function I started with. So I know that first function is even without having to graph it. Okay. Next one. I'm going to take that g function and I'm going to plug in the argument negative x to see what I get. And so this would be negative x squared plus 1 over negative x to the 5th power minus negative x. So my numerator is, of course, just positive x squared plus 1. My denominator is going to be negative x to the 5th plus 1. So is this even, odd, or neither? Oh, sorry, plus x. Yeah. Negative x to the 5th plus x. Yeah, this is odd. It's a little tricky. But you've got to be able to recognize that factoring out a minus sign from the denominator actually gives you the negative of the function that we started with. And so that makes it odd. All right, the next one says 2 raised to the power x. Is that one going to be even, odd, or neither? Yeah. So if I plug in negative x, that's not this function I started with, and it's not the negative of the function I started with. That's something else completely, so we say this is negative. Okay. So there's a shortcut, and the shortcut takes a little while to explain, but this is the shortcut. Remember on the first day of class, we talked about just the natural numbers. And all the natural numbers are either even numbers or odd numbers. And we said, if I add together any two even numbers, the sum is an even number. If I were to add together any two odd numbers, the sum is an even number. And if I were to add an even number plus an odd number, I'll get an even number. And you could memorize this table, but without having to memorize it, you could also just try out really small even and odd numbers. Like you could try 2 plus 2 and 2 plus 3 to test out whether these rules work. And it has to work for all of the numbers the same way. So there's rules for adding and subtracting even and odd numbers. There's rules for multiplying even and odd numbers. Well, if you add or subtract fractions, I'm going to say that so many times. If you add or subtract functions, adding and subtracting functions. Adding and subtracting even functions will give you an even function. Won't mess up the symmetry. Adding or subtracting odd functions will give you an odd function. Doesn't mess up your symmetry. But if you add or subtract even and odd functions, it gives you a function that has neither symmetry, right? What I want you to notice is that I matched the colors here intentionally. Because adding or subtracting numbers follows the same rules as multiplying or dividing functions. Dividing an odd function divided by an odd function is going to give you an even function, it turns out. And so that's a way to help you memorize these rules in case you wanted a shortcut. And multiplying numbers works the same way as composing functions. So if I compose an odd function with an odd function, it's going to be an odd function. I can remember that if I think about multiplying an odd number times an odd number, it gives me an odd number, and so on. So what I want to say is, when you're doing your homework and you've got like exercise 4 in your homework, or if this is a test question, you can just use the test, right? Plug in negative x into the argument and see if you get the function back, or see if you get the negative of the function. That always works. But as a shortcut, I might think this is an odd function divided by an even function, and an odd function divided by an even function should be odd. Right? the next one, we said cube root of x is an odd function. X is an odd polynomial. And odd divided by odd should give me an even function. This is an odd function composed with an odd function. And that should give me an odd function. Right? Composing functions, odd and odd, that should give me an odd function. And then lastly, I've got an odd function composed with an even function, because the absolute value is an even function, and according to my table, this should be an even function. So, if you can remember how to make the table, or if you can remember this table of rules, then this is just a little shortcut for determining even and odd functions. You don't have to graph them, you don't have to do the tests. They follow these nice arithmetic rules.